So we move on to transient over voltages, surge protection and insulation coordination. And we talk about transmission lines, but this discussion applies to distribution lines as well. And they are spread over hundreds of thousands of miles. And so what could be the cause of over voltages here? We'll see that, but we need to protect against those over voltages. Otherwise, they could possibly damage our power apparatus here. So we will look at the causes of these over voltages here. So there are two main causes. One is this lightning strike here. The other one is switching of extra high voltage transmission lines. So we all are familiar with lightning strikes, and this lightning strike can be represented as a current pulse, and the waveform is shown here, that it rises from 0 to some peak value in this time t1 here, and then it tapers off and reaches half this peak value at this time t2 here. And this peak current magnitude that has been recorded as high as 200 kiloamps, but generally we talk about 10 kiloamps to 20 kiloamps peak here. And we try to protect the apparatus against the over voltages that result because of such a lightning strike here. So to protect transmission lines against lightning strikes, we have so-called shield wires. So let's look at the construction of this transmission line tower. We have three phases here, one phase, two phase, and three phase here. But in addition, on top we have these so-called shield wires right here. And these shield wires are connected to the tower, which in turn is grounded. All right, so the idea is that these shield wires, they are essentially at the ground potential, and they protect the transmission line conductors from lightning strikes. And usually we talk about this 30-degree zone of protection here. Okay, and like I mentioned, that these shield wires are grounded through the tower to ground, and we would like to keep the tower footing impedance as small as possible. And we should also note that not all transmission lines have shield wire. It depends upon the company philosophy, the zone in which that the company is located. Maybe it's not as prone to lightning strikes, then why have this extra expense of shield wires? So it's a matter of economic decision here. So what happens is that when a lightning strike occurs to a shield wire, this current would travel in both directions, and then it will pass to ground through this tower and the tower footing impedance over here, right here, like this here, right? So this large current flowing through this impedance then would raise the potential of this tower. And then there could be a flashover between the conductor and the tower through the insulators, okay? And so long as insulators then heal, this is called self-restoring, there's no problem. But there could be a follow-on current, and if that may itself be not a problem, but if the insulators are damaged, then we have a permanent damage, so to speak, and they have to be repaired. Okay, but if they are self-repairing, then there's no problem. Okay. This lightning can strike to the conductors themselves, and then you'll have traveling waves, proceeding in both directions, and as a consequence, this insulator strings which insulate the conductors with respect to the tower, they may flash over, or these traveling waves may reach the termination where, let's say, you have transformers and so forth, and you better have surge arresters there to not let the voltage get too high, otherwise the equipment may be damaged. So we'll look at surge arresters. So we talked about the lightning strikes, but we also have to worry about switching surges, because when we are looking at high voltage and extra high voltage transmission lines, like 500 kV line here, and for example here, if you open up this line because of some fault, let's say a short circuit fault, the next step is to close that line back into operation, right? So when you close that line, and let's say the other end of this line is open, then the voltages can reach as high as 2 per unit. So you apply closing in 1 per unit over here, and then there's traveling waves, and the open circuit voltages at the other end could be as high as 2 per unit. Okay, so you have to make sure that there are surge arresters which prevent this transmission line and whatever apparatus may be connected from getting damaged here. So one option, of course, is to use so-called pre-insertion resistors. So insert this line back into operation through resistances, which are then bypassed. Okay, so you can put a resistance here and then a switch like this here. So when you initially insert this line, the resistance is in circuit, and then you can bypass that by closing this circuit over here. Okay, so quite often for very high voltage lines, these pre-insertion resistors are used to minimize the over voltages that will result at the other end here. So we have to, we can of course talk about this transpose perfectly balanced situation where we saw that the surge impedance given by L over C, ignoring the losses. If it's perfectly transposed, you can calculate what the inductance of this line would be depending upon the distance between 3 conductors. You can calculate what the capacitance would be, and the velocity of travel, the speed of travel, is given by this here, which will turn out to be the speed of light. Okay, so if you ignore the losses and stick to this scenario here, you come up with these traveling waves traveling at the speed of light here. But situation is not symmetric. The transient disturbances are unbalanced in the sense that there may be a lightning impulse to only one of the phases. Okay, and similarly, the transmission lines are not perfectly balanced. Okay, because they may not be transposed, and so there could be a zero sequence current here, as mentioned here, and we have to worry about the impedances for positive sequence, negative sequence, as well as zero sequences for different frequencies. Because in this transient phenomena, we are not talking about 60 hertz. We are talking about impulses here, which contain all kinds of frequencies. So here's a plot that I got from the source 2 over here, and it shows the positive and zero sequence. Positive and negative sequence are the same. So positive and zero sequence inductances and resistances as a function of frequency here. Okay. So if you have a nice transient analysis program like this EMTDC, electromagnetic transient program, then all these features are available in such programs here. So, whatever example we have, we can then calculate over voltages based on that here. We can just put it into this transient analysis program, and we'll have our answer. So the next thing is that we need to worry about insulation to withstand these voltages, and so we should be able to withstand, this insulation should be able to withstand certain amount of over voltages for a certain period of time. Okay, and it's dependent upon many factors as listed here, and the power system apparatus, it can be characterized as self-restoring and non-self-restoring. So I talked about that this transmission line insulators, that they could be self-restoring, whereas so even if these insulators flash over, when that follow-on current goes to zero, they may come back to their original state. Okay, but then you have equipment like transformers and generators. Their insulation is non-self-restoring, because if there is a flashover there, then it's kind of permanently damaged, and then it's a very expensive proposition to repair it. So we have to take into account this insulation consideration here, and it's a sort of a statistical and probabilistic approach here. You cannot afford to protect against all outcomes, all events. So you have to make a decision as to how much insulation to have to protect under most common eventualities. So there are different types of definitions here of insulation. One is this basic insulation level, so-called BIL. And here, if you have a lightning impulse, as shown here, and the level of insulation is specified as the peak that it can withstand, and so that's BIL, and it's this type of characteristic here, where the peak reaches its peak at 1.2 microseconds and tapers off to 1/2 the value in 40 microseconds here. So that's taken as a standard to define BIL. So you can see that for a 345 kV transformer, its insulation BIL, basic insulation, may be as high as 1175 kV. And this is defined as a function of time here, okay? Because, well, we'll talk about this here. The other basic insulation is for that peak waveform that I described, but then there is also switching insulation level, and this is caused by switching over voltages when we switch the transmission lines. And these voltage pulses are longer in duration. They may reach peak in, let's say, 250 microseconds and may taper off to 1/2 the peak value in 2500 microseconds. So they are longer lasting pulses, and therefore the same insulation would have a lower switching insulation level as shown here, okay, because the insulation level depends on two things, the magnitude as well as the duration. Okay, so this is since switching surges are of longer duration, the insulation level, switching insulation level, is smaller for a same type of insulation for which this BIL was over here. Okay. Then we have chopped wave insulation, where the voltage impulse reaches its peak, but then beyond its peak, it's chopped to 0 in 3 to 4 microseconds. So in that case, the same insulation level, same insulation may have higher chopped wave insulation level over here. Okay, you can see, but the time duration is small too here. So that is the insulation of the equipment, but then we also have surge arresters, and the role of the surge arresters is to not let the voltages get too high, so that there could be a damage to that arrestor. So they essentially act like a Zener diode. So if voltage were to rise beyond a design value, they will begin to pass very large currents, and they'll essentially clamp the voltage to at that level. So you can see that the voltage current relationship is highly nonlinear, to the power 26. So they are basically, they clamp the voltage. And so they should be able to dissipate this energy without being damaged, because when the current is flowing through them, and after that they should come back to their normal state once everything is restored here. So these series arresters should keep a margin of at least 15 to 20% between the voltage level at which they start conducting and the insulation level. Okay, so that is what is called as insulation coordination. You take the insulation of your equipment and you coordinate it with surge arresters. So there is at least 15 to 20% margin, if not larger. Okay. So this pretty much brings us to the end of this module. We went through pretty fast. Here we looked at protection against short circuit faults. We looked at causes of over voltages. We looked at insulation needed to withstand these over voltages. And we looked at surge arresters and how to coordinate these surge arresters with insulation level. Thank you.